Hello, and welcome to the very first episode of Learning Cool Things with Elastra. So, today we're going to be learning about something amazing. It's bigger than your mind could ever comprehend, farther away than you could ever travel, and brighter than any earthly light. It's simply out of this world. Stars. Stars. What are they? So, I just see most people to think of they're the little white dots in the sky, that come out at night, and sometimes you can see they make pictures, it almost looks like, or shapes, constellations. And, they're in outer space, they must be super far away, which they are. And, a lot of people even know that our sun is a star, which is all true, it's all really cool. But at the same time, when I think of stars, and when I think many others think of stars, I think of this colossal gaseous sphere. And yeah, it's far away, but that's a little bit of an understatement. It is so incredibly far away, like light years and light years and light years. And even though it's so far away, it is so big and so luminous that we can still see it. We can still see its light, even from our tiny little planet so far away from it. And at the very core of the star, what's happening is nuclear fusion. So the atoms are forming and fusing together to make new atoms, which then can be released when the star explodes into a supernova. So all of that, all of both explanations, and some of what I haven't said yet, is what we're going to be learning about. And we're going to be learning about how amazing our night sky can really be. As I aforementioned, stars are insanely far away. Our closest one to us is our sun, being 150 million kilometers away. But the next closest to us is over 4 light years away, which means that if anything like a rocket ship was traveling there at the speed of light, which is over 300,000 kilometers a second, even if it went there constantly, it would still take over 4 years to get there. So, you might be thinking, since stars are so far away and we obviously can't travel there, how scientists have even figured out their distances, and so precisely too. Well, the answer to this is something called parallax. And it may be a little complicated, but I have an example here to try to explain it simpler to you. So here's a little visualization of how they measure parallax. In position 1 of Earth, it records how they see the star in the sky compared to the nearby star, and they just show the background stars there. So then 6 months later, after Earth has made half of a rotation around the sun, they record again where they see the star. And that little tiny shift in difference between them, the apparent change, is the stellar parallax. So that little shift in the star's position is what a stellar parallax is. And a stellar parallax is measured in something scientists call a second of arc, which written down is represented as what looks like 2 quotation marks. And so 1 second of arc is equivalent to 1 over 3,600th of a degree, which is the same size as if you saw the diameter of an aspirin tablet 2 kilometers away. So it's a really small shift. And there's another form of measurement of distance called a parsec. And a parsec is the distance to a star whose parallax is 1 second of arc. And 1 parsec is equal to 31 trillion kilometers, which is the same as 3.26 light years. Okay, so we may have found out a star's distance, but there's no possible way that we could find out its composition, what it's made out of, right? Wrong. We can find out what it's made out of, and that is all thanks to stellar spectra and wavelengths. Stellar spectra is basically just meaning the light that comes from stars, so starlight, and starlight has many different wavelengths. And a wavelength, to try to describe it, is if you think of a color wheel, it has all those colors. It's kind of like that, except if it was laid out all in like big one strip. So on one end of the spectrum, there is red, and it goes all the way till there's on the other side where there's blue. Atoms are the building blocks of everything because they make up all matter. And if you don't already know, the structure of an atom, like how it would look, is there's 3 main components to it. There is a proton and a neutron, which together form a nucleus that is in the center. And then orbiting around it is electrons. Here's a little example. And so, for how this has to do with stellar spectra, is it was found that atoms are responsible for the different types of wavelengths in the spectrum. And electrons, there is a thing called binding energy. So that means that it's the energy required for the electron to remove it from the atom. Also, if just the precise amount of energy is either added or taken away from a specific electron, then they can either go up or go down levels. And here is a little example video to show you that. Chunky the electron starts off on the first level, but once getting enough energy from Ebby, can he go on to the second level. Once there, he can go back down, but once he does, he emits a pellet of light called a proton. When an electron jumps down from a higher level to a lower level, what it shows is also known as emission lines. And each element has its own unique emission lines. So this is why when studying spectra and wavelengths and emission lines, that they can tell what elements a star is made up of, because they already know what emission lines and wavelengths each element looks like because they have done tests on it on Earth, all these elements that are on Earth. So when they compare these emission lines compared to the ones that are shown in the wavelengths of stars, then they can be like, oh, that has hydrogen and that has helium, and they can find out the composition of stars. When trying to find the surface temperature of a star, so how hot or cool the star is on the surface of it, we just have to go back to how we found out the composition of a star. Because using those same emission lines, we can find out how hot the star is. So scientists have figured out, they saw that there was some slight differences in the emission lines, and this turned out because it was varying levels of surface temperatures based on which star it was. They have separated these temperatures into 9 main groups. From hottest to lowest, it's being named O, B, A, F, G, K, M, L, and T. And actually, a fun fact is a way that many university students remember this order and all those letters is by an acronym. They say, "Oh, be a fine guy, kiss me, love to." And despite popular belief on the wavelength spectrum, like I've said, how it goes from red all the way to blue, the hottest stars are actually blue because blue is the hottest wavelength, and the coolest stars are red, being on the opposite side. When you look up at the night sky, you might be able to tell that some of the stars look like they are at different brightnesses. Some are stronger looking, some are weaker. Part of this is because, of course, even though they may all look like they're in the same area in the sky, they're actually very far differences away from each other. So some may be way closer, making it brighter, some may be farther, making it look fainter. But some of them are also way bigger and way more luminous, meaning more bright, and hotter, and they shine more. So that can also affect how some look. And in fact, some of the super bright stars you see in the sky, they may not be stars at all. Those could actually be planets. So astronomers find out apparent brightness, the way that the star appears in the sky, from its luminosity, the actual amount of light it gives off in space each second. And many other stars, how they help to figure out the luminosity is based off the one we know best, our star, the sun. So many stars are stated in terms of the sun's luminosity, L. Our sun's luminosity is in fact equivalent to 3.85 times 10 to the power of 26 watts, which may sound like a bunch of jumble, kind of does to me too, to be honest. But what that basically means is that's the same as 3,850 billion trillion 100-watt light bulbs shining all at once. There are many different types of stars, and they range from about 0.0001 to a million times as bright as our sun. And the farther away a star of luminosity is, the less bright it appears, and that is known as the inverse square law. There are also two main things that are important when talking about the luminosity of a star. There is apparent magnitude, which is how bright the star appears in the sky, and then there's absolute magnitude, which is the measure of its luminosity. And like I said, how they can be at different brightnesses because they're different levels farther away from Earth. The way that they can find out scientifically how bright it actually is for it to be equal is they say the apparent brightness of a star is how luminous it would be if it was 10 parsecs away. So then with distance canceled out, they can see how luminous the star is compared to others. The average human lifespan is about 80 to 85 years or so. The average star lifespan? A few billion years, at least. There are some stars that are predicted to be a few trillion years old, but it hasn't gotten that old yet because the universe is still only 14 billion years old. Insane, right? So though it is a bit of a lengthy process, we are going to have a quick little explanation of the birth and deaths of stars. Stars are in fact made from the elements and matter that is just drifting around in space, called interstellar dust. And so there are times when interstellar dust, it clumps together so much by gravity. Sometimes this is also caused when a supernova, which is after a star dies. But if there's a different star that died in a supernova, then what's left of it can be interstellar dust. It's just remnants and pieces of the once was star. But from those pieces can actually create new stars. So with a very long time of that star remnants and interstellar dust and gravity and everything, heat all mixing together, dancing and conjoining and collapsing in itself, eventually a baby star is born. And of course, there were many stars being created billions of years ago, and we know this because there are many stars out there that are billions of years old, like our star that is 4.6 billion years old. But in fact, there is still stars being born today, and we have evidence of this. We can see it in the Orion Nebula, nebula being normally a big birthplace of stars, and the Orion Nebula is 1,500 light years away from us. Throughout the billions of years, a star can have a magnificent life of burning hydrogen from its core and twirling around and zooming through space around a black hole in its galaxy, most likely. But once it finally comes for the star's time to end, it doesn't happen as quickly as it does for humans or other creatures. It in fact can take another thousands or millions of years for its ending life to put to an end. Once all the hydrogen in its core has completely burned out, this is when it really starts to happen. So as an example, I'm going to use our sun, because that might be easier to imagine. So our sun is a yellow star, and it's about medium sized. But once all its hydrogen in the core burns out finally, in about 5 billion years, so no need to worry. But once it does, then it's going to start expanding. And when I say expanding, I mean expanding a lot. It's going to get so big that it's going to eat up all the first 4 planets in our solar system, and then suck in almost all the rest of the planets in the solar system because of all the gravity it has, because of how ginormous it's gotten. And once it gets that big, then after thousands or millions of years, eventually then it's going to suck and collapse. It's going to get so small, about the size of Earth even, but it still has all that matter in it. So even though it's got so small from the big, huge star, it is so dense. And so that extremely small, dense star is now considered a white dwarf. Some stars, if they have enough oomph in them, I'd say, before they become a white dwarf, or even after they become a white dwarf, they can explode outwards in a supernova and create a planetary nebula. And like I said, that is part of where interstellar dust and the remnants of that star come in, and they can make new babies. Those white dwarfs are predicted to eventually turn into black dwarfs, but again, the universe isn't even hasn't been around long enough to reach that level yet. Some stars, like red giants, and then what are eventually super red giants, they can explode outwards into a super planetary nebula, but the reaction from them and the amount of energy that ensues is just so immense that it just all collapses in on itself, but far greater than just becoming a white dwarf. It becomes a singularity called a black hole, where nothing, not even light itself, at the speed of light, can escape. There's so much more that I could say about stars, and far more than I probably even know. But there's so much about it that people have written whole books about it, so unfortunately we can't get all of that into one video now. But this was just an introduction and a little basic learning so that hopefully now you know some of the understandings of the distance, the composition, the temperature, the luminosity, and life and death of stars. Thank you for watching, and I hope that next time you look into the night sky, you can think of just how wondrous and complex those little white dots really are.